everyone. So the topic we'll be discussing in this lecture is paging. Okay. So this is a important concept. This is the heart of this particular chapter. So with so the topic we'll be discussing is demand paging. Okay. So with demand paging, what happens in the sense a page will be brought into the main memory only if it is required. Unless and otherwise it is not required, the page will not be moved to the main memory at all. By this, what happens in the sense there will be less IO in terms of swapping a page. So when you want to swap a page, you need not swap the entire process, but it is just enough to swap that particular page. Okay. So here even we don't use the term swap, we use the term page replacement. Actually, you should not use the term swapping, you should use the term page replacement. So as we are just replacing one or two pages, there is a less IO requirement and unnecessary IO operations in terms of swapping is avoided. And each process needs only less memory. Even though the entire process may occupy a lot of memory, but we are not going to bring the entire process into the main memory. We are going to bring only few pages. So the memory requirement is reduced. Hence, there will be a faster response time and more processes can be in the main memory simultaneously, which increases the degree of multiprogramming. Okay. We can say that demand paging is similar to paging with swapping. Demand paging is similar to paging, the normal paging. Okay, normal paging which we discussed in the last chapter. So demand paging is nothing but the normal paging with swapping. To the normal paging you add swapping, then that is called as demand paging. But this swapping is what? It is not the swapping of the entire process, but it is just the swapping of the pages. So you can call this as a lazy swapper. So we can call this as a lazy swapper. That is, we are just going to swap a page, and that too the page will be swapped only if it is required. Okay, here we are talking about swap in, swap in. So a page will be swapped in from the disk to the memory only if it is required. Because of that, it can be called as lazy swapper. But even then, the term swapper is misleading. Even then, the term swapper is misleading because generally the term swapping is used to swap the entire process. But here we are not swapping the entire process, we are just swapping the required pages. Okay, as we are swapping the required pages, this concept can be called as paging with lazy swapping. But still the term swapping is misleading, so we don't use the term swap, rather we use the term pager. Okay, instead of using the term swapper, we use the term pager. Okay, so the key takeaway is demand paging is nothing but paging with swapping. Still, to refine that, it is not just paging with swapping, it is paging with lazy swapping. That is, swap a particular page, swap in a particular page only when it is required. As long as it is not required, let it be in the hard disk. Only if it is required, swapping, and swap only those pages which are required. So because of that, this technique can be called as lazy swapper. But again, the term swapping is misleading because generally swapping is associated with swapping the entire process. So instead of using the term swapping, we use the term pager. Okay, instead of using the term swapper, we use the term pager. So this is a brief introduction to demand paging. Okay, let us see how it actually works. So the pager. So the pager brings only those pages into the main memory which are required. It will not bring all the pages. Only the required pages will be brought into the main memory. Now now the CPU will generate a logical address. So, so as we have already discussed, the CPU will be generating the logical address. Say this is the CPU. CPU will generate the logical address. This logical address, once it is generated by the CPU, the memory management unit will check. The memory management unit will check whether the page associated with this logical address, it is in the memory or not. Okay, memory resident means CPU is creating some logical address. The memory management unit will check whether the page associated with this particular logical address is available in the memory or not. If it is available in the memory, then just identify the respective frame number from the page table and convert the logical address to physical address and access it. So it is very similar to non-demand paging. Non-demand paging means normal paging. So normal paging, like what we have discussed in the last chapter, it is similar to that. If under this condition, that is, the CPU is creating a logical address, and the page corresponding to that logical address is already available in the main memory, means the working of demand paging is similar to non-demand paging, that is ordinary paging. That is, identify the frame number corresponding to this particular page, convert it to physical address, and then use it. Okay. So this is case 1. Case 1 is if the particular page is memory resident, that is, it is available in the memory. If the page is not available in the memory, then what to do? Okay, so this is case 2, that is, CPU is creating a logical address and the page corresponding to that particular logical address is currently not in the memory. Okay, the page corresponding to that logical address is currently not in the physical memory, right? Then what should be done? Okay, so basically it means that in the logical memory, it is referring some page, say page, okay, say page 5, okay, but that particular page is not available in the physical memory. That particular page is not available in the physical memory. In between you have memory management unit which checks which page is available and which is not available. So this particular page P5, it says that it is currently not in the main memory. So this situation is called as page fault. This situation is called as page fault. That is, the CPU is creating a logical address and the page corresponding to that logical address is not currently available in the physical memory. This situation is called as page fault. So when a page fault occurs, then what to do? So what to do in the sense, the memory management unit should detect and load the page into the memory from the storage. That is, from the hard disk. If there is a page fault, whenever there is a page fault, the CPU, that is the memory management unit, should identify that page from the disk. Okay, from the hard disk it should identify that particular page, and that page should be loaded into the physical memory. After loading it to the physical memory, then the page table also should be updated. That is, this particular page which is previously missing, now it is brought into the main memory and it is in so and so frame number. Like that, this is the page number and this is the frame number. Like that, the page table also should be updated. This is the job of the memory management unit. It should do that. Okay, and it should do all these things without changing the program behavior. Because of that, the program behavior should not change, and also the programmer need not do any change in the code. Okay, programmer, it should not affect the programmer. Programmer will assume that all pages are available in the physical memory. In that context only, he works, because for him, because he sees only the logical memory or the virtual memory. He don't know that there is the logical memory is different from physical memory, and there is some memory management unit which is mapping logical memory to physical memory. All these things he don't know. So whenever there is a page fault, it is the job of the memory management unit to identify the page from the hard disk and to bring it to the main memory and to allocate a particular frame and to update the page table. All these things the memory management unit should do without affecting the program behavior and without expecting the programmer to do any extra coding, right? So for doing all these things, some additional hardwares are required in memory management unit. What are those additional hardwares that we will discuss? What are the additional hardwares required in memory management unit? In the sense, mainly the memory management unit needs an extra hardware, and this hardware is called as valid or invalid bit. Okay, that is in the page table. In the page table, so normally with normal paging, the page table contains only what? The page table contains only the frame number. It contains only the frame number for the respective pages. Page 0. Okay, so this first so this is index. Okay, in the index, so the page table is index with respect to page number. If it is page number 0, it is available in which frame? 7th frame. Page 1, it is available in which frame? 2nd frame. Page 2, it is available in which frame? 15th frame. So this is a normal page table which contains page 3, it is available in which frame? 12th frame. Like that it contains. But to support demand paging, some additional improvement should be done for memory management. So some extra hardware is required. The extra hardware is, we are adding one more bit to the page table, one more column to the page table, and this column is called as valid or invalid bit. This column is called as valid or invalid bit. So it is shown in this diagram. So the page table contains the frame number and there is a valid or invalid bit. So whenever the valid bit is set, if it is V, so the valid bit will hold either V or I. V represents valid, I represents invalid. If it is V, it means that particular frame, I mean the frame corresponding to that particular page. So this is frame number, this is page number. Page number 0, which frame? Page number 1, which frame? Page number 3, 2, 3, 4, like that. Okay. So it means that if the valid bit is V, then it means that the frame corresponding to that particular page is available in the physical memory. If it is I, if it is I, then it means that the page corresponding, the frame corresponding to that particular page is not available in the physical memory. Okay, so that is what the valid or invalid bit means. Okay, so I think it is clear. So the additional hardware which is added by the memory management unit is, it adds one more bit which is called as valid or invalid bit to the page table. Page table is indexed with the page number. Page numbers are contiguous allocations like 0, 1, 2, 3. So it maps a page number to a frame number. If the valid bit is set, it means that the frame number corresponding to the particular page number is available in the physical memory or the main memory. Whereas if the valid bit is I, it means that the frame number corresponding to that particular page number is currently not available in the main memory or the physical memory. Right? Okay. So what to do? So if the valid, if it is I, then what should be done? That we will be discussing. But before that, here it is a better example. So this is the logical memory, okay, for one particular process. We are taking only one process. Normally logical memory will be bigger than physical memory. In this diagram, it is as if the logical memory is smaller than the physical memory, but that is not the case. This is only a partial view of the logical memory with respect to one particular process, say P1. So this particular process P1, it contains this many pages. How many pages? 8 pages are there. Totally this process P1 contains 8 pages. Okay. But currently out of these 8 pages, only 3 pages were in the main memory. The pages A, C and F are in the main memory. Remaining all pages are in the disk. Right. Now this is the page table. Okay, memory management unit uses the page table to map the logical or the virtual memory to the physical memory. Okay, so the page corresponding to the frame corresponding to page 0, is it available in the main memory? That is page A. Is it available? Yes, it is available. In which frame it is available? It is available in frame 4. So the valid bit is V. Okay. Similarly, the page corresponding to the frame corresponding to page 1, is it available? No, it is not available. The page B is not available in the main memory. Okay. So so the page, the frame corresponding to page 1, it's not available in the main memory. So this location contains empty and the I bit is set. It is I. It means this particular page is not in the memory. The frame corresponding to this page is not in the memory. Okay. Page C. Is it available in the physical memory or the main memory? Yes, it is available. So the frame corresponding to page 2, it is available. Yes, it is available in which frame? Sixth frame. So the valid bit is V. Okay. So like that it proceeds. Okay. So the frame corresponding to page F, it is available in the physical memory. Okay. So the frame corresponding to page 5 is 9, okay, which is page F, and it is V, that is it is available. Remaining all it is not available. So wherever there is not available, it is I. So whenever, if those pages were referred, if CPU creates a logical address, say CPU creates a logical address 3, so it means page number 3, but the frame corresponding to the page 3 is not available. So this will create what? This will create page fault. So this will create something called as page fault. It means that page is not available. Okay, in that case, what the memory management unit should do? It should retrieve that page from the hard disk. Which page it is missing? The page corresponding to page 3. Okay, the page corresponding to uh, virtual address 3. Okay, virtual address 3 is page D. Okay, so it should bring page D to main memory. It may allocate some location, say it brings page D to frame 13. Okay, page D, it moves page D to frame 13. Then it should add that here. It means that uh, page, what do you call, page page 3 of virtual memory or logical memory is added to which frame? It is added to frame number 13. Okay, it is added to frame number 13. Okay, what is page 3? Sorry, what is page 3 is D. So D is in frame 13. Okay, and also it should make I to V. So whenever there is a page fault, the memory management unit should do all these things. That is, first it should identify the page from the hard disk, move it to the main memory or the physical memory, and then update the page table. So these are the tasks that should be done by the memory management unit whenever there is a page fault. For doing this, memory management unit needs an extra hardware, and that hardware is valid or invalid bit which is added into the page table. Okay. So this is the extra hardware which is required for demand paging, but which is not required for normal paging. So this is what we have just discussed. If the first reference to a particular page will result in a, so whenever there is a page fault, say the operating system wants, say the CPU is creating an logical address, and that logical address corresponds to the page 1. Okay, page 1, that is the logical address 1. Logical address 1 refers to page B. Okay, page B, is it in the memory? No, it's not in the memory. Okay, so then there is a page fault. Okay, so whenever there is a page fault, it will create a trap. Whenever there is a page fault, so this particular logical address 1, it is not available in the page table. How do we know it is not available? Because a valid invalid bit is I. So it is a page fault it will create. So the page fault is nothing but an trap to the CPU. Trap is what? Hardware interrupt. So the page fault will create a trap to the CPU, which is a hardware interrupt. Okay, so once that trap is created, then the CPU will fetch the respective page. So in this case, it is page B, the respective page from the hard disk, and it will move to the main memory. Some frame will be allocated for that. In this case, the frame 11 is allocated, and now once again the page table will be updated to pay updated to accordingly. It will be updated. It is now the page number, the frame number corresponding to page 1 is 11, and the valid or invalid bit will be changed to V. Okay, so all these things will be done. So the point I'm making is, whenever there is a page fault, first a trap will be created. Okay, and uh, and when the trap is done, okay, the operating system will check whether Oh, there is one more thing. Yeah. So so whenever there is a page fault, there will be a trap. Okay. So the trap is an interrupt to the operating system. Then the operating system will check whether it is a valid reference or not. Okay. Whether whether it is a legal reference or not. Okay. So legal in the sense what? Say here legal in the sense this particular process P1 it can access only these pages A, B, C, D, E, F up to H. It cannot access the page say J. There is a page J. Can process 1 access this particular page J? Is it eligible to access? No. So that is called as illegal access. That is called as illegal access. Okay. So the page, say there is a page J that is also not brought into the main memory, but that page not corresponds to process 1. So it corresponds to some other process 2. Now if the logical address created by process 1 through the CPU is referring to this particular page J, which not belongs to this particular process P1, then that is called as illegal access. That is called as illegal access. Okay. So when the page fault creates, so this will also create a page fault. So this will also say the page number J. It may in the logical memory it may associated with logical address 9. So logical address 9 also it may be I. It may be I. So it means it is not. So this will I means it is invalid. So it will create a page fault. Okay. So immediately when the page fault is created, a trap will be created to the CPU. So first CPU what it will check in the sense. First CPU what it will check in the sense it will not directly bring that page to the main memory. First it will check whether this process is eligible to access this particular page or not. It will check that. So in this case, if process P1 is trying to access the page 9, it is illegal. It is illegal. Okay. If it is an illegal access, it will abort. It will abort the process. It will terminate that process. That is, it will terminate process P1 because it is trying to access an illegal page. So it may be a malware, it may be a virus program, or it may be trying to attack your system. So such access will be aborted. Okay. Only if it is an legal access, only if it is a legal access, and if it is not available in the memory, then it will be brought from the hard disk to the main memory. Okay. So that is what this particular statement means. So whenever there is a page fault, it will a trap will be created to the operating system. So first the operating system checks whether it is a valid reference or not. If it is invalid, here invalid in the sense the more appropriate term will be illegal. If it is a illegal reference, that is if the particular process is not supposed to access that particular page, in that case it the operating system will abort that process. It will terminate that process. Okay. If it is not an illegal access, then it means that it is legal. The access is legal, but it is not just in the memory. Then you should move that to main memory. Then find a free frame. Then first find a free frame in the main memory. Okay, main memory contains in the previous diagram. If you see, main memory contains some locations may be free. So which are the free frames? Identify the free frame, and then swap the page into the free frame from the hard disk. Okay. And reset the table entry, that is set the validation bit to V. Okay. And once again restart that particular instruction. So this step is also very important. Once again restart that instruction, whichever the instruction which caused page fault, again restart that instruction, because you have to start that again, then only that access will become successful. Okay. So these are the steps which are involved in demand paging. Okay. So to summarize, so in demand paging, what we are checking, the only required pages will be brought to the main memory. So if the page is available, if the particular page is available in the main memory, then its working will be very similar to that of normal paging, that is non-demand paging. But if the page is not available, then it will create a trap to the operating system, and the operating system will check whether it is a legal access or not. If it is an illegal access, the operating system will abort that particular process. If it is a legal access and if it is not in the main memory, then find a free frame and move that particular page from the hard disk to the main memory, and set the validation bit to V in the page table, and again restart that instruction, because once again that instruction should be executed, which created the page fault. And now this time it will execute successfully because the respective frame for the corresponding page is added to the main memory. Okay. So this diagram overall explains clearly like what happens when there is a page fault. What happens when there is a page fault? Okay. So the CPU is creating a logical address. So that is what the step 1 says. Okay. And logical address refers to a particular logical address, but that particular logical address, the page or the frame corresponding to that logical address is currently not available in the main memory because the I bit is set, so it is invalid. Okay. It is not in the memory, so it will create a trap to the operating system or the CPU. Okay. It will create a trap to the operating system, and the operating system will check whether it is a legal access or not. Okay. If it is a illegal access, the process will be aborted. If it is not an illegal access, if it is a valid access, then the operating system will identify that particular page from the hard disk. Okay. And it will load into the main memory. That particular page, it will be loaded into a free frame in the main memory. Once it is loaded, so these are the various steps. Okay. So the loading is fourth step. Once it is loaded into the main memory, then the fifth step is to update the page table. That is in which frame number it is loaded. So this particular page is loaded at which frame number? Maybe this is second frame, and it is loaded in which page number? Maybe this is sixth frame. Then 6 will come here, and previously this I invalid will be converted to V. Okay. So that is uh, uh, fifth step, and as the sixth step, restart this instruction. So these are the various steps involved in handling a page fault. Okay. So the first step is the logical address is not available in the page table. That means the frame corresponding to the logical address is not available. The second step, it creates a trap to the operating system. Third step, identify the particular page from the hard disk. Fourth step, load it to the empty frame, load it to an empty frame in the physical memory. And fifth step, update the page table with the particular frame number and convert the I bit to V bit. And sixth step, again restart that same instruction so that now it can execute successfully. Now if it is restarted, for the particular page we have a frame number and the valid bit is set. So with this frame number you can identify the physical address and you can access it. So this is how the concept of demand paging works, right? Okay. So here there are certain things which we can further discuss. That is, there is a concept called pure demand paging. There is a concept called pure demand paging. So what is that? So what is normal demand paging? Normal demand paging in the sense, initially when a process is loaded, maybe the operating system will identify some important pages and it may load that important pages into the hard disk, into the main memory. Okay. So for a particular process, the operating system may identify some 10 pages. So that 10 pages may be loaded into the main memory in some frames. Page 1, page 2, up to page 10 may be loaded into the main memory in a non-contiguous fashion at some empty frames into the it's not exactly 10, it depends. Okay. So that is what happens with normal paging. Okay. And then when the CPU creates the logical address, if the page is available, it executes normally. If the page is not available, then it will create a page fault and then it will create a trap. All these we have discussed. Okay. So that is how a demand paging works. What is pure demand paging? Pure demand paging, what it means in the sense, initially don't load any page to the main memory. Okay, when a new process, you are going to execute a new process P1, it's going to execute. So none of the pages corresponding to P1 will be available in the main memory. 0 pages. Okay. CPU creates a logical address. CPU creates a logical address. Say first address CPU creates. But obviously none of the pages were loaded. So whatever the address it creates, whatever the logical address it creates, it will result in a trap. It will result in a trap. So identify that particular page from the hard disk. Identify that particular page from the hard disk and load it to the main memory. Okay, now one page comes. Say page 1 is added into some frame, say frame 10. Now CPU creates second address. So that is also not available, add that. Page 2 is added to, identify that from the hard disk and add it. Page 2 is added to say frame 15. Now CPU creates the next address, page 3. So it is also not available. Again, identify that from the hard disk. A trap will be created, identify from the hard disk and add it. So page 3, say it is added to frame 20. Like that, you add whenever there is a, what you call, whenever there is a page fault to identify. So initially, not even one page will be added. So that concept is called as pure demand paging. Okay. So then you may think that in that case there may be many page faults. No, that is not the case. There will not be many page fault because of a concept called locality of reference. What is locality of reference? Locality of reference means normally if you take any program, a program contains some multiple functions. Okay, so there may be a, say there may be a function, say function 1. Okay, so this function 1, if currently if this function 1 is executing, this may have some variables or some arrays, some stacks or some data structures it may have. Okay, so if this program contains some 100 instructions, these 100 instructions will be only working on these variables. Here, if you are using an array, these 100 instructions, out of these 100 instructions, maybe 20 or 25 instructions will be referring that arrays. And whatever the variables declared in that function, it will be using that. So it may not use, it will not, it is not that these arrays will be used only once. It may used several times during the execution of this function. So that concept is called as locality of reference. Okay, maybe once you may get input for the arrays, then you may be changing the content of the array, then you will be displaying the array. So all these are what? You are accessing the same arrays again and again. So once if that array was brought into the main memory, uh, for first time there will be a page fault. But after that, the same array will be accessed several times. So that concept is called as locality of reference. Because of locality of reference, uh, even if you go with pure demand paging, it will not create that many page faults. Yes, initially it may create many page fault. Some initially it may create some number of page faults. Once sufficient number of pages were added into the main memory, then gradually the page faults will decrease. Okay, as long as that procedure is executing, right? Again, if the control moves from that procedure to another procedure, once again the page fault may increase. Okay, so that is called as locality of reference. To support demand paging, as we already discussed, some extra hardwares were required. One is the valid and invalid bit, and then second is some swap space is required in the secondary storage device, and also there should be an ability to restart that instruction, because finally whenever there is a page fault, we do what we do. The trap will be created and the page will be identified. It will be moved to the main memory, and then finally we restart that instruction. So that restarting ability should be added. So that is the hardware requirement. Okay, so this is the overall working of demand paging. Okay. Okay, so pure demand paging means this: in the extreme cases, start the process with no pages in the memory, and each uh, page initially it will create a page fault, and then load one by one page. So that concept is called as pure demand paging. So now uh, fine, we'll stop here about this discussion. So demand paging is the crucial concept. Okay, so you should understand this lecture very thoroughly, because the entire chapter is depends on this lecture. So make sure that you are thorough with this, right? Let us stop here. Thank you.